Hello everyone. So as of now we have completed hello everyone. So this is the problem that I have given in the previous class, that is a homework. I'm not going to give you the in detail solution, but anyway I'll give you the clue how to solve this. So the first thing that is, why wide swing current mirror? It is not a point of my 5 transistor OTA. Just I am taking because I have taken this 5 wide transistor current mirror in telescopic structure. But at least we should understand how to analyze this circuit. It can be the part of your interview, because in some places they ask these things. So this is a basic a part of big circuit, but it is important. So what see, actually we always try to work in lesser voltages. So I mean to say that is that for particular amount of current that we want to copy here, we want the minimum value of this node. If I say this node x, for minimum value of x node, if my structure is properly copying this current I in, it means it is a good structure. If we are losing any extra voltage, then we can see, because we have fixed amount of VDD. Always in any structure, whatever the design we have, we may have the design of 1.8 volt. We always have the fixed VDD rail. We always have some value of VSS, maybe here 0 volt, and in between we have this room of 1.8 volt. And out of this 1.8 room, if we lose, I'm talking these things in sense of amplifier, if we lose more values in current mirror and input pair just to keep them in saturation, and what is the need of that structure, because we will get very less swing. For a rough example, if I'm consuming means 500 millivolt in upper transistors, maybe the low transistors, and if I'm consuming 500 millivolt in lower transistors, which are input pair and current means current transistor. So what is left to me? There is nothing but only zero point 0.8 is left to me. 0.8 peak to peak is left to me. So it means whatever the gain of transistor, you cannot apply a means bigger input, because you know your swing at output is limited. So if you will apply the more input or more peak to peak signal at input, it means your output will be saturated. So there is a no use of that. If anyway I am giving this headroom to 400 to upper devices and 400 to lower devices, anyway I am saving more headroom here. So what is the swing I can have now? 1 volt. This is my 1 volt peak to peak. That's why this headroom is very important. Anyway, this is the structure of current mirror, is nothing but a bottom structure. If it is itself consuming 400 millivolt, then it is good from this example perspective, what I have given here. And if it is consuming 500 millivolt, then it is a lesser important for us. So this is the way we have to reduce this Vx amount, or means amount of voltage that is making this current just copying. So okay, now I think this you understood. So what is the value of this node? This node value is for particular input current. This value is simply VGS of 1. If I call this transistor 1, yeah. So this node is at what? If I call this node X dash, and this is called Y dash or Y. So what is the value of Y? From the two side, if I look from this side, if I look from the transistor 1 and 3, then Vy minimum can be what? So if I consider for time being both the both the BGS same, then what you can see, this is nothing but V overdrive of 1 plus VTH. I am not marking here 1, just I want to tell it how much we are losing. V overdrive plus VTH of 2. So overall the minimum value that we will have 2 overdrive plus 2 VTH. So this is the requirement of minimum value from the side of transistor M1 and M3. So what should be the exactly minimum value of Vy from the side of M transistor 2 and 4? Yeah, from this side, what should be the value? Vy minimum equal to V overdrive of 2 plus VGS of 4, which is again overdrive of 2 or 4, overdrive of 4 plus VTH. So it is 2V overdrive plus VTH. I'm considering all the means VGS same so that I can compare in better way. So from both the side we can see that if I'm going through, if I'm seeing from the side of 1 and 3, we are losing one more VTH. But actual need of this minimum VY voltage is that it should be 2 overdrive plus VTH. So it means we are losing one extra VTH here. If we are losing one extra VTH, then what will the effect? Okay. So we are losing one VTH here because here it is going to VTH. So from here we can see that what will be the Vx minimum for this value. What will be this Vx? Vx minimum from this calculation will be what? If I am going through transistor 1 and 3, so minimum value will be Vy minus 1 Vt. It means 2 overdrive plus Vt. But actual need of this voltage is what? Just 2 overdrives. So anyway we are losing this thing here. But here we will see that this minimum value is my VGS itself. Okay. So this node is what? What is the minimum value of Vx? Vx minimum is, so this is the minimum value at node X. So minimum value plus this VGS is the minimum value of this node Y. Yeah. So from Vy minimum is what? Vx min, that is my V overdrive 1 plus VGS of 3. So if I am considering all the transistors identical, it will be V overdrive plus VTH. It is nothing but 2 overdrive plus VTH. From here I can see the value of this node Z, Vz min equal to Vy minus 1 VT. So that is 2 overdrive only. This is my requirement. This is my requirement. 2 overdrive, because we know that 1 overdrive is going here, okay, and 1 overdrive is going upper device M4. 1 overdrive is going here and 1 overdrive is going here. So this value minimum consists 2 overdrive voltage. So more than that is just a waste of voltage here. Okay, so this is I think enough for this value. And for input current, input resistance, you can see here this is a node Y here and this X dash. They are fixed nodes because of current VGS is fixed. So these are fixed nodes, so there is a no small signal fluctuation. From there you can calculate the input current, or what next you can do, you can apply any test source here and you can exactly analyze the direction of current, not direction, exactly you can calculate the V test or I test, and for both the cases. Okay, so now you'll again go back on 5 pack. So in this video I'll tell the important thing about the 5 pack OT is that, okay, so I think some of you may know the basics, so I'll go not through the complete basic, but yes, I will tell about the concept of noise first. For any resistor R, this is a noisy resistor. If it is a noisy resistor, I can say what? I can model the noise voltage in the series of this resistor. Now this is noiseless. So the value of this is nothing but 4 kT. Also we can model noise current in parallel of this noiseless resistor. This current is what? IN bar. This is nothing but 4 kTy. So in general its unit is volt per root hertz and its unit is ampere per root. In terms of power, noise power can be represented like this, which is nothing but 4 kTr, where the unit is voltage square per hertz, and here noise power current in terms of current 4 kTr, 4 kT by R ampere square per hertz. And the relation between IN and VN square, averaging current, square bar means averaging current, is nothing but R square. This is the relation that I am using. So this is for resistor. For transistor, noise can be modeled like two things. This is my transistors. So I can model this current as the noise of this transistor M. Okay, so this can be modeled as IN average. For this it can be 4 kT gamma GM. This is noise current, and gamma in general we can use 2 by 3, not an empirical number, it can be something else also, but usually we have seen this thing 8 kT by 3 into G of the transistor. So this is the noise current. So the also noise, we can model the noise as a series input voltage as well. So what is this value of this? So in general, for any transistor, input voltage to output current, what we write, output current to input voltage, there is a parameter called GM, which is nothing but a GM of transistor. So if I know the current, then what will be the noise voltage? It is nothing but, so this is a square root of this. This is the root of this. Okay, so what I will write, IN divided by GM, or in terms of voltage square, it will be IN square by GM square. So it will be 8 kT 3 into GM divided by GM square. So it will be 8 kT by 3 divided by GM. So this is the noise voltage at the input. Root mean square, or mean square value, that is the power, which is 8 kT by, sorry, not by. So these are the general values I will use throughout this discussion. Okay, so now I don't have the resistor in the 5 pack. So when we will calculate the noise contribution at output, why I am calculating at the output? Because the input referred offset is important, we know, but the point is that by calculating at the output, if we divide it by means gain, if we are calculating the noise voltage at the output, we can divide it to the gain of the circuit, and we will reach at the input referred noise voltage. And if we are getting the output current, noise current at the output, it means by dividing it to the GM of the circuit, we can have the input referred noise voltage. Okay, so this is my circuit of 5 pack. So now we will see the individual contribution of the noise. So when we will do the noise analysis, we will just short these inputs, and we will only consider the noise across the transistor. Okay, so if I am considering first M naught, for M naught, if I am saying that, because direction does not matter for the noise current or voltage, that's why sometimes I am making it as stars. But yeah, if I am considering this current, noise current due to M0 is going downward, just I am considering, if I am considering the direction is not that much important for the, because we usually consider the mean square values, the power terms, so direction is not that important. But if I am considering one direction, that we have to stick on that particular only. So okay, So if I consider this current is going down, then what you can see, the main thing is that from any particular node, we have to see that who is the contributor of this I and not. We know that this is my VGS is 0. So high, actually this is a high impedance node if I am looking from the top side. Also from this node is providing me 1 by GM resistor, this node is providing 1 by GM resistor, and this is the high impedance node. So overall I can say here no current is going, no noise current is going inside this transistor M naught. So the entire I node is coming from this way. So yeah, so this actually I've taken the direction reversed just to tell that what is the looking of impedance. So for this source, what is the current? IN naught by 2, and here also what is this? IN naught by 2. So this current just it is copying here. This is IN naught by 2, and the entire current is flowing. Whosoever is entering here is going to this transistor M2. So overall I can see what is the short circuit current, short circuit noise current due to M naught. What is this? This is 0. So overall we can see that this device is contributing to no noise at the output. Okay, so this is another contribution of this analysis is for. You can see from here there is a no contribution of noise of this transistor current pair transistor, not current pair. This is the bottom current transistor has no contribution in the output noise. Now we will see the input pair devices. I will draw the structure again so that there can be clarity can be maintained. Okay, wait. Just here is the loads. I am not that much worried. We know just it is a current mirror. So I can see here mirror. I don't draw every time. So this I want to see. That is my output short circuit noise current due to 1, 2. Any of the one I will calculate, and later we will see the overall effect. So I'll go through the effect of this. Yeah, upside I will say that we are looking what 1 by GM resistor. This side we are giving the high impedance. So at this node I have to see. First I have to model the current. That is like this. IN of 1 averaging out. So at this node we can see that there is a 1 upon GM this side, 1 upon GM top side, and this is a high node. Bottom side is a high. So yeah, at this node if I am seeing, then what we can see that this side this transistor M1 itself is taking means is showing 1 upon GM impedance, and this transistor M2 is showing 1 upon GM impedance at this node. So I'll explain this thing clearly. So we can see that at this node or this node, same thing, 3 paths are there for this current IN, which is I am considering direction this. So half of the current will go up and half of the current will go down, which will flow through this M2. So what is this? IN1 by 2 will go this transistor. Here no transistor, no current will flow, and half will go to this transistor M1. So at this node, what will happen in this node? This current is going complete IN, and from this side it is going IN by 2. So who is coming from upper side? This is coming at IN by 2. Okay, so this is mirrored IN by 2, and half is going up from this side. So at this node we can see ISCN1 at output is nothing but complete IN1. Similarly, ISN2 at output is IN2. You can do the analysis. So at for the inputs, this is the contribution M2, M0. It is, we have seen M0 here, then M1 and M2 contribution this side. Okay, so we have analyzed that in output current noise till now we have seen that for M0 there is no contribution, and for M1 and M2 entire noise current is going to the output. So they are completely contributing to the output noise. So we will see next slide then what is the contribution of current pair devices, and later on we will see that how to minimize this noise, what are the factors responsible to reduce this noise, and how it can be minimized. Okay, so here we'll see the contribution of mirrors. Okay, so now we will see the mirror device. Just make ground because I don't need any other input except from the noise of the transistors. This is my output short circuit current due to 3,4. I'll calculate for 1, then we'll double it. So I'll consider this transistor noise. Let's say I want to give the direction to upside. So this is 3. Okay. Now we have to see through things. What is the impedance of this node? This node has impedance. This side is order of rds of 1, and this side or upper side, or can say this side, is the impedance of. Okay, so I should a little place it down. If I make little less later, then we can see from this side the impedance is 1 by gm. So it can be seen that this is a high impedance node. So the entire current that is coming from this transistor itself and revolving like this, so inside the transistor. So what is the current in the transistor? The complete IN is flowing, IN3 is flowing across the M3. So there is a no current, noise current is going. So I mean say this entire IN3 is copied here, no current this side, 0 ampere. So ISN is completely IN3. Okay, IN3. Similarly, you can see that for the transistor M4, the complete current is coming to the output. Yeah, complete current is coming to the output. You can see here. So overall, ISCN4 equal to IN4, the input. So overall, total noise contribution, this is the contribution of pairs. Here I will see. If there is any confusion how this will come, you can see here. If I consider the noise of transistor M4, you can see here. If I consider the noise of this, there are two paths. This is a short circuit path, and this is the high impedance path. And this is the short circuit path. So the complete IN4 will flow to the output short circuit. So this way we can see the total contribution. Now I will see the total contribution, and one more thing that I will write here. The noise parameters are not added at out, means arithmetically, so they are added like root mean square. So how will they get? It is IN1 square plus IN2 square due to M2, IN3 square plus IN4 square. Okay, so this way you can see this is nothing but 4 by 3 sorry 4 no 8 by 3, it did 8 by 3 KT GM1 plus 8 by 3 KT GM2 and so on. So from here if I take 8 by 3 KT common, GM1 plus GM2 plus GM3 plus GM4. So one more thing that we know for the 5 pack, which is GM1 equal to GM2 and okay. So total short circuit noise current, at output short circuit noise current square is what? 8 by 3 KT 2 GM1 plus 2GM3, that I can write. So this is the output short circuit current of the noise. Now I want to see what is its input referred noise. So what is the input referred noise that I told you previously, which is nothing but output short circuit current square in noise divided by GM square, and GM of this structure we know nothing but a GM of input pair. So it is nothing but 16Y plus GM3 divided by GM1 comma 2 square. They are same, so I can say 1 only. So from here we can see 16Y 3 KT divided by GM1. So here you will see 1 plus GM3Y GM1. So this is the total input referred noise of 5 pack. Input referred noise of 5 pack or 5 transistor OTA. 5 pack or 5 transistor OTA. Okay. So how to reduce the noise? I'll take on this page only. How to reduce the noise. So from the expression we can see that there is a contribution of the input referred noise, that I will say in square, that is input referred noise voltage square, is nothing but a function of GM1 and GM3. So it is a function of all the devices, or it is a function of device transconductance. If we can manage higher GM1 and lower GM3 or 4, then we can optimize the noise. But there are different things that are related with GM1 and GM3. So we cannot increase GM1 anyway to the much extent, or we cannot reduce GM3 to the much extent. There are other aspects going to be disturbed. So this is the one way that we can analyze the noise. And how they can ask this thing in interview? They will not maybe interested in the entire derivation, but you must have the knowledge of what trend in the design should be considered so that we can minimize the noise. So exactly you must be aware of this expression. Well, you must be aware of this expression and how this transconductance of mirror devices are affecting your noise, and how the transconductance of input pair are affecting the noise. So this is the concern about the noise, and whatever the noise value it is given, you can just link with that. If I want to suppress my noise under this at some unit frequency, this is my 10 nanovolt, then we have to think how to adjust my transconductance values. Okay, so and this is enough for this video, the noise perspective. Later I will tell in the coming video about the offset also, because in this video I will do the offset, it will be long enough. So I think this is enough. Thank you.